everyone. In this lecture, we will be covering antiderivatives and indefinite integration, and we will see just how those two things are related and kind of the exact same thing. So our goals in this lecture are for us to be able to find general solutions of differential equations, which is a term that we will define in this lesson. We also want to be able to use indefinite integral notation, and we're going to learn some basic integration rules, and we'll combine those two things together to be able to find not derivatives, but now antiderivatives, the opposite of derivatives. And then finally, we will learn how to find the particular solutions to differential equations, and we will find that using initial conditions or different specific values that were given to us. So we start our conversation with antiderivatives. So let's start off and no longer think about taking derivatives, think about going in the opposite direction. So this time we want to find a function that I'm going to call capital F, and I want to find that function so that the derivative of that function would be 3x squared. So I'm looking for a function that when I take the derivative of it, I would get 3x squared. Well, we can use our knowledge about derivatives and the power rule to conclude, well, that function could be x to the third, because we know that if I take the derivative of that function, capital F, that I have decided to be x to the third, that the derivative of x to the third is 3x squared. Drop our exponent of 3, decrease our exponent by 1, so we have 3x squared. When this happens, we can say that the function capital F is an antiderivative of the function that we started with. So we started with this 3x squared, and we said, well, what do we take the derivative to get that? And we concluded that we take the derivative of x cubed. So x cubed is an antiderivative of 3x squared. On the flip side, 3x squared is the derivative of x cubed. Notice that I keep saying is an antiderivative. I have not said that x to the third is the antiderivative of 3x squared, because there's many functions that I can take the derivative of and get 3x squared. Yes, I can take the derivative of x cubed and get 3x squared, but I could also take the derivative of x cubed minus 5 and still get 3x squared, because we know that the derivative of this minus 5 would just go to 0, since the derivative of any constant is 0. So similarly, if I considered the function x cubed plus 97, that function would also have a derivative of 3x squared, because the derivative of x cubed is 3x squared, and the derivative of 97 is 0. So all of these functions are antiderivatives of 3x squared. In fact, I can pick any constant c, and this function x cubed plus c, I could choose the number pi, I could choose the number 101, any constant c, it's going to be an antiderivative of that 3x squared. So our formal definition is that a function capital F, we're typically going to call our antiderivatives capital F, a function capital F is an antiderivative of lowercase f if when we take the derivative of capital F, we get lowercase f. This definition is followed by a theorem that says if we have an antiderivative, then we can generate more antiderivatives, different antiderivatives, by just adding constants, which is kind of like what we did here. We found x cubed to be the first antiderivative that we happened upon. And then I just started adding constants. Here I added the constant -5. Here I added the constant positive 97, and I still had more antiderivatives for that function. So that's what theorem 4.1 says. So theorem 4.1 says, really, it's not that there is one antiderivative, there is a family of antiderivatives, because that constant c could be any real number. So for example, let's say we know that the derivative of x squared is 2x. So the family of all antiderivatives of 2x would look like x squared plus any constant c, right? Because if I take x squared plus a number and start differentiating that, we're always going to get 2x, because the derivative of x squared is 2x and the derivative of a constant is 0. So we call this constant capital C the constant of integration. And the family of functions, when I just leave that c written generally and do not specify a specific value for that c like we did up here, that family of functions is called the general antiderivative. It is also the solution to the differential equation g prime is equal to 2x. So let's talk about this equation. This equation g prime equal to 2x, that equation is asking us to find all functions that when you differentiate that function, you would have 2x. And those functions look like this: x squared plus any constant. Generally speaking, the formal definition of a differential equation is that it is an equation that involves x, y, and the derivatives of y. So I know you don't see a y here, but the function name and y are kind of interchangeable. So this equation here, g prime equal 2x, is kind of like the same equation as y prime is equal to 2x. So I have told you that the derivative of what we're looking for is 2x. So what is it that we were looking for? Well, it was something that looked like x squared plus c. So here are some other examples of some differential equations. Y prime is equal to 3x. This is asking us find all functions y such that when you take the derivative of that function, you would get 3x. And here's another example of a differential equation that just uses a little bit different notation because we know that y prime and dy dx mean the exact same thing. So now let's look at our first example. We want to find the general solution meaning that we will have this plus c. We have not specified what the value of c is for the differential equation dy dx is equal to 2. To solve this, I need to start off and just find one function whose derivative would be 2. Well, a function whose derivative would be 2 would be the function y is equal to 2x. Now, according to theorem 4.1, let's go back and look at that theorem. We have found one antiderivative. Theorem 4.1 tells us that in general, all of the antiderivatives will have this form: the antiderivative that we found, and we can add any constant c to it. So generally speaking, the general solution to this differential equation would be y is equal to 2x plus c. And we can check this answer because let's see what happens if I were to differentiate both sides. So if I apply the derivative operator to both sides of this equation, we will need to take the derivative on the left side and on the right side. On the left side, the derivative of y is simply dy dx, or y prime. On the right side, we're taking the derivative of a sum. We're going to take the derivative term by term. The derivative of 2x is 2, and the derivative of any constant c is 0. So I don't even have to write that. And this is exactly what we started with. So we did the opposite of taking the derivative. We found the antiderivative. Now, when we're solving a differential equation of that form, dy dx is equal to f of x, it's convenient to rewrite the equation by, I'll show you how we get it. If I take this equation and I multiply both sides of this equation by dx, then I've just canceled the dx out on the left side of the equation, and I'm left with dy is equal to f of x times dx. Okay, so that's where this is coming from. dy is equal to f of x times d of x. Now, the operation that we go through in order to solve this equation is called antidifferentiation, which is synonymous with an indefinite integration. Now, the symbol that we use to denote that we want to take the antiderivative is this integral sign here. So this integral sign here, think of it the same way that you think of this ddx, right? We know that this ddx right here means take the derivative of what's to follow. This integral symbol means take the antiderivative of what's to follow. So here is some notation for us. Here's our integral symbol. What's on the inside of that integral symbol is called our integrand, which will always be followed by a d something. It might not be dx, it could be dt, it could be d theta, but whatever the variable is that follows the d tells us our variable of integration. So the same way that this d dx tells us to take the derivative with respect to x, This dx tells us to integrate with respect to x. And when we do integrate, what we get is an antiderivative that we know from theorem 4.1. We can then add any constant of integration to it. So now that we have got some notation under our belt, let's go look at some basic differentiation rules. So we've already discussed briefly this inverse relationship between taking a derivative and taking an antiderivative. So looking in at some of these rules, on the left side here, we have derivative rules. So for example, we know how to take the derivative of a constant to get 0. The flip side of that would be integrating 0 would give you any constant c. These first sets of rules show us the similarities between differentiation and antiderivatives. The same operations that we have when we take derivatives, the same properties that we know how we can pull constants out, how we can separate with sums and differences. We have the exact same thing going on here on the other side when it comes to integration. So if I'm trying to integrate an expression that has a constant in it, I could kind of ignore that constant at the beginning, pull it on the outside of the integral, and integrate as normally. I want to talk about this last rule here. We know how to take the derivative of x raised to some power n. We drop our exponent and we decrease our exponent by 1. Now we're going to talk about, well, how do we undo that? How do we take the integral of x to the n? So we do the opposite. Instead of decreasing our exponent by 1, we increase our exponent by 1. And instead of bringing that exponent down and multiplying it, we divide by what that new exponent was. There is a caveat here that this rule does not apply when n is equal to -1. Later on in this course, we will see how to integrate when x is equal to -1. That table is followed by another table of differentiation rules and integration rules, antiderivative rules for trigonometric functions. So we'll just look at one example briefly before we go on and eventually apply some of these rules. So consider the secant function. We learned earlier in this course that the derivative of secant is secant tangent. So the opposite of that, the antiderivative, would be that the antiderivative of secant tangent is the secant function. And notice that I do have this plus c because, again, we could have any constant value there for that constant of integration. So let's look at a second example. We want to describe the antiderivatives of the function f of x is equal to 3x. Well, to get the antiderivatives of the function f of x, I am going to integrate f of x with respect to x. So inside of my integral with respect to x, I will be putting the function 3x. Now, very similar to how we started with derivatives, I'm going to take my time here and show you how these integral rules can be used. So we saw a rule earlier that tells us if you're integrating something that has a constant in it, that you can pull that constant out in front of the integral. So I am now going to apply that rule and pull this constant of 3 in front of that integral so that I'm now only integrating x with respect to x. So do not forget what this means. This means to find a function whose derivative is x, okay? So we are trying to integrate x to the first power. I'm going to scroll up to our integration rules, and I'm looking at this one in particular because this one tells me how to integrate x to some power. In this case, our n value is 1, and the rule tells me you need to increase the exponent on x. So the new exponent on x is now 1 plus 1, and you need to divide by your new exponent. So you need to divide by 1 plus 1. And do not forget to add on that constant of integration. So we are left with, oh, and I dropped my 3. So don't do what I did. You see this 3 I pulled out here? I dropped that. So I'm going to go in and add that back in front of this, leaving us with 3. I'll simplify because 1 plus 1 is 2, and we are dividing by 2, and then I will add c. So our answer for the antiderivatives of the function 3x is that they look like 3x squared divided by 2 plus c. To give us some perspective and tie that back in with what we were talking about earlier, if I graph the function y is equal to 3x squared divided by 2, in this case, I have chosen my c value to be 0. Alternatively, I could choose my c value to be 3, or I could choose my c value to be -6. So notice that I'm not talking about one particular answer. We have built a family of functions. All of these functions that we see there, all of these graphs, if we take the derivative of any of those functions, we will get 3x. That is what it means to be the family of antiderivatives. Now we're going to look at example 3 that is going to require us to rewrite our integrand. Integrand means what is on the inside of the integral. It's going to require us to rewrite our integrand before we are able to apply these derivative rules. So we've seen things like that before. For instance, really quickly, if I ask you to take the derivative of the square root of x, very likely you would rewrite it as x to the 1/2 so that you could see that 1/2 exponent before you apply the power rule. So you rewrote it before you differentiated it. Similar thing is going to be happening here. We're going to rewrite our integrand before we actually integrate it. So I'm going to start off and just replace that square root of x that's in the denominator with an x to the 1/2. And then I'm going to continue to simplify this by separating this into two separate fractions. I'm going to take it as the x in the numerator divided by the x to the 1/2 plus the 1 in the numerator divided by the x to the 1/2 dx. Remember that this x in the top there has an exponent of 1. Rules of exponents tell us that to simplify dividing with exponents, you subtract. So I'm doing 1 minus 1/2 to be left with 1/2 plus. And then this term I'm going to rewrite because we know that 1 over x to the 1/2 is the same thing as x to the -1/2. And then I'll make sure to add on my dx at the end. So I want to be crystal clear here. So far in this problem, we have not done any calculus. All we have done is algebra to take this expression and rewrite it as this expression. Because this is something that now I can scroll up and look at my integral rule that tells me how to integrate x to some power and apply this rule to get our answer. So that rule tells us, well, one, I will point out before I even apply that rule, that we're integrating a sum. The sum rule for integration tells us that I could take the integral of that one sum and split it up into two separate integrals that are being added together. So first I will do that just so we can see that rule in action. So this is the same thing as the integral of x to the 1/2 dx. Every time you write an integral symbol, you need to put a dx or whatever your variable of integration is, plus the integral of x to the -1/2 dx. So now let's actually start applying the rule. The rule says that we take the current exponent of x, we add 1, and we divide by our new exponent, and that we need to add c. I'm going to move this plus c. If I were you, I wouldn't write that right now. I'm going to move it. Plus, let's go on and integrate this second integral. Tells us that we take the current exponent of x, which is -1/2, we add 1, and we divide by the exact same thing. And we also need to add on that constant of integration. So the reason I said that I was going to move that one is because I don't need two separate constants of integration, right? A constant plus a constant is just a constant. So I really only need to write the plus c once. As long as I have it, then I'm good. So I don't need to write that twice. So now let's just simplify this. X to the 1/2 plus 1 is x to the 3/2. So our denominator is also 3/2. And then in the second term, -1/2 plus 1 is a positive 1/2. So we have this, and now we will simplify this because dividing by 3/2 is the same as multiplying by 2/3. Because we know to divide by fractions, we multiply by the reciprocal. And in our second term, the x to the 1/2 in the numerator, I'm going to rewrite simply as the square root of x. And dividing by 1/2 is the same thing as multiplying by 2. And I'm going to make sure to not drop my constant of integration. I will mention that you could rewrite that x to the 3/2 power as the square root of x cubed, just using properties of exponents. To refresh your memory if you need it, I will remind you that generally speaking, x to the a over b is the same thing as the bth root of x to the a. So I had x to the 3 over 2, the same as the square root of x cubed. And so we have our answer there. Now let's look at example 4. We are integrating 1, 2, 3 different terms. So we could break that up into 3 different integrals, which is how I will begin. Notice that after each integral, I'm making sure to put a d theta. That's a notational issue that is important. You cannot write an integral symbol without having a d theta. So think of this and this as a pair, right? These have to go together, and whatever you put on the inside is what you want to integrate, whatever you want to take the antiderivative of. When I look at our first term, I see what we want to integrate. It has this constant of -5 in front of it. We learned that we could pull that constant out in front of the integral. So I am just going to quickly rewrite that with that constant pulled out in front. And I'll go ahead and rewrite the other integrals that we had there as well. And now let's go look at our integration rules to see how do we integrate cosecant cotangent. So looking at my trig integrals, I see that the integral of cosecant cotangent is negative cosecant, which makes sense because we know that the derivative of cosecant is negative cosecant cotangent. So I'll bring down my constant of -5. And then for my integral there, we just saw in our rules that this is negative cosecant. I haven't put the plus c because I will put the plus c at the end. I don't need to write 3 separate plus c's. Second, we have the integral of secant squared d theta, integrating with respect to theta. So we're asking ourselves, what do we take the derivative of in order to get secant squared? If you are familiar with your derivative rules, you probably know that it is tangent. I will go up and show you that rule here that says that the integral of secant squared is the tangent function. And that is because the derivative of tangent is secant squared. And then finally, our last integral, we're integrating simply just theta. That's kind of like just integrating x. So I wouldn't look at a trig rule for that. I would look here because we're integrating just theta to the first power. So in this case, our n is, I'm pointing at the wrong thing. I should be looking over here, you all, right? Because we're not taking derivatives right now. We're taking integrals. So we are integrating just theta. So it's like we're integrating theta to the first power d theta. So it's like our n is 1. So I'm going to be applying this rule to integrate theta. That rule tells me that I need to increase the exponent on theta by 1. So the new exponent on theta is 2. And I also need to divide by the new exponent and add my constant of integration, c. And then the last thing I'll do is I'll just clean this up because I have these two negatives here. So I'm left with my final answer as a positive 5 cosecant theta plus tangent theta plus theta squared divided by 2 plus our constant of integration, c. Example, we are integrating t minus 4 quantity squared. We need to begin by first expanding out this integrand. So I'm going to take this t minus 4 and actually square it out, which leaves us on the inside with the t squared minus 8t plus 16. That's after you FOIL and combine like terms. So I did all this, and then I combine my like terms. And now we know that we can break this up into 3 separate integrals. So I am now integrating each term individually. I have some terms with some constants like this 8 and this 16. Constant multiple rule tells us that I could pull those constants out in front of these integrals, and then I will actually start integrating and taking antiderivatives. So this just leaves a 1 on the inside of this integral, which I could write or don't have to. For the first integral, we're integrating t squared. That is t to some power. Basic integration rules tell us to increase the exponent by 1 and to divide by the new exponent. It tells us to add c as well, but we'll just do that at the end. We're going to use the same rule to integrate t, which is the same thing as t to the first power. Integration rules tell us to increase the exponent by 1 and to divide by the new exponent. I'm going to bring down the constant of 16. Technically, the 1 that's on the inside of this, you could think of as a t to the 0. Well, let me go back to that. This 1 right here, this is asking, what do we take the derivative of in order to get 1? We take the derivative of just t. So this is simply 16t. Now that we're done integrating, I'll make sure and add my constant of integration. What I was going to mention earlier is that this right here is like the same thing as integrating t to the 0, because we do know that t to the 0 is the same thing as 1. Anything to the 0 power is equal to 1. Integration rules tell you to increase the exponent by 1 and divide by the new exponent. So this really is just t for that integral. This is where we get that t right there from. Last thing I'm going to do is just simplify this because I have this negative 8 over 2. And that leaves us with our final answer. We have already seen that when we're integrating something, generally, we get infinitely many solutions, right? Because we get these plus c's on the end, and that c could be any possible real constant number. So all of these solutions are simply differing from each other by a constant. So for example, let's say that we are trying to solve the integral of 3x squared minus 1 dx. So we know that that means we need to integrate 3x squared with respect to x and then subtract the integral of 1 with respect to x. To integrate the 3x squared, we could pull the constant of 3 out in front of the integral of x squared. And then we're left with minus the integral of 1 dx. Let's actually start integrating now. We still have this constant of 3. To integrate x squared, we increase our exponent by 1 and divide by our new exponent. I'm going to subtract, and then the integral of 1 is simply x, and we will add our constant of integration c. I can simplify this and simply be left with x cubed minus 1 plus c. So we know, and I showed you on Desmos earlier in this video, what happens when we choose different values of c. So for example, here, all of these graphs are variations. Oh, I don't know why I wrote a 1 right there. This should be x cubed minus x. All of these graphs are variations of this with different c values. So for instance, when c is 0, the function hasn't moved at all. If I let c be 1, it would move the function up 1 and be that function there. What if I let c be negative 3? Well, it would move the function down 3, and it would be this function down here, right? So all of these functions, when you take the derivative of them, you would get 3x squared minus 1, right? So they're only differing from each other by some constant value. Each of these is a solution of the differential equation dy dx equals 3x squared minus 1. Now, when we actually deal with real world applications of integration, most of the time we're not interested in getting this infinite family of solutions. We are more interested in one of these functions in particular. So for example, we may be asked to solve a differential equation, but we may be given some additional information that is called an initial condition. They may say something like, hey, I do want you to find the antiderivative of this, but when you find all of these functions, I'm particularly interested in the one that goes through the point 24. So here is the point 24. So I'm particularly interested in just one of those functions. So how we find that, which particular function we want, which is why it is called a particular solution when we are given an initial condition, how we find that is we start off the exact same way we did. We actually go through the anti-differentiation and get a general solution. So we're at the point now where we have found this general solution. So now I'm going to use this initial condition where you came to me and said, hey, I don't want all of these solutions. I want the one that particularly goes through the point 24. I want the one that when you plug 2 into your answer, so I'm now substituting 2 into this general solution. So I would have 2 cubed minus 2 plus c. I want that to equal 4. And solving this equation will solve for C and tell us which of these in this entire family are we particularly interested in. So let's go ahead and solve this. We have 8 minus 2 plus C is equal to 4. That's 6 plus C is equal to 4. Subtract 6 from both sides to see that C is equal to negative 2. So the particular function that we were looking for would be the function capital F of x is equal to x cubed minus x, not just plus any C, but the one where the C is a negative 2. So when we go through some problems with solving differential equations, right, because this is a differential equation, we may see some additional information like this, which is called an initial condition. We integrate as normally, get a general solution. A general solution does not have a specified C value. It just has an arbitrary constant of integration. And once we have that general solution, we plug in our initial condition and we solve for C. Once we know what C is, we put it into our general solution to get our answer. So let's look at another example. We want to find the general solution of this differential equation, and then we're going to take it a step further and find the particular solution that satisfies this initial condition. So to start off, this means find the function capital F whose derivative is 1 over x squared. I will rewrite 1 over x squared as x to the negative 2. There's an inequality in here that x is greater than 0. Please do not be confused by that. That is simply making sure that we are avoiding domain issues, because we know that we could not plug 0 into this function since that would give us 0 in the denominator. We'd be looking at a vertical asymptote there. So let's get started and find capital F of x. The function that we are looking for would be the antiderivative of f prime of x. So we are going to be integrating that 1 over x squared, and we're going to do it with respect to x. I'm again going to rewrite that as an x to the negative 2 dx. At this point, we are ready to use this same rule that we've used several times so far that tells us how to integrate x to a power. It tells us to increase our exponent by 1 and divide by our new exponent and to add the constant of integration c. So now I'm just going to rewrite this because this is the same thing as negative 1 over x plus c. So here I have my general solution. And in fact, I'll write it on the next line. Capital F of x equal to negative 1 over x plus c is our general solution. But remember, this is a family of solutions, right? C could be 1, 2, 3, 4, 5, 6, 7.5, 9.2, any constant value. They have taken it a step further and asked us to find the particular antiderivative in this entire family that satisfies the initial condition. So I am particularly interested in the function that when I go in and replace x with 1, which I have just done, I will get out 0. That is what this means. That when you replace x with 1, you will get out 0. It will all be equal to 0. So let's solve for c. This says that negative 1 plus c is equal to 0, which implies that c is equal to a capital 1. So our particular solution no longer has this arbitrary constant of integration c. It is the function capital F of x is equal to negative 1 over x, where the c is particularly a positive 1. In example 7, we are simply being asked to find a general solution. Notice that there is no initial condition like there was in example 6. I'm going to start off and just rewrite this differential equation in the equivalent form of dy equal to 5 cosecant squared x dx. So I just multiplied both sides of that equation by dx. That is a technique called separating variables. So what that means is that now I have all my y's on one side of the equation and all my x's on the other side of the equation. I'm ready to introduce an integral so that we can take the antiderivative of both sides of this equation. On the left side, the integral of dy is simply y, the function that we are looking for. Because remember, when this problem started, it said your goal is to find a function whose derivative is 5 cosecant squared. So now let's work on integrating on the right side. And I'll have that constant 5. We'll still need to integrate this cosecant squared dx. If you are very well versed with your trig differentiation rules, you may know what that antiderivative is. If not, look back up here. The antiderivative of cosecant squared is negative cotangent plus c. So we have that y is equal to 5 times negative cotangent x plus c. I'm just going to rewrite that so it looks a little bit better. That would be negative 5 cotangent x. So that's our answer. Let's check our answer. So to check our answer, let's take the derivative of what we got. So we got y is equal to this, differentiating. That means that dy dx is equal to the derivative of negative 5 cotangent x plus c. Well, the negative 5 is a constant. We can kind of pull it out and ignore it for now. The derivative of cotangent, we would need to look back to, I'm not 100% sure which lesson this is in. I think this is in 2.3. Yep, look at that. There we go. The derivative of cosecant is negative cosecant cotangent. Oh, sorry, we're not taking the derivative of cosecant. We're taking the derivative of cotangent. Let's go back to 2.3. The derivative of cotangent is negative cosecant squared. So the derivative of cotangent is negative cosecant squared x. And the derivative of this constant c is simply 0, so I don't have to write that. And very perfectly, this leaves us with 5 cosecant squared x, which is exactly what we started with. So yes, we did find a function whose derivative was 5 cosecant squared x, which is exactly what we wanted. We're going to do the exact same thing in example 8. I'm going to start off and just separate my variables. So I would have that dy is equal to 6x to the negative 4/3 minus 2x to the negative 8, and all that will have a dx. So I did two things in one step here. I multiplied both sides by dx to cancel that dx out on the left side, and I also rewrote this term as 2x to the negative 8, because that'll make it a little bit easier for us when we come in and start taking our antiderivatives, which is what we are going to be doing now. On the left side, the antiderivative of dy is simply y, the function that we are looking for. Here, we're integrating two separate terms. I'm going to integrate this term by term. So I do have this constant 6 that will stay there. Let's talk about how to integrate this x to the negative 4/3. Integration rules tell us we need to increase our exponent by 1 and divide by our new exponent. Here, we have this constant of negative 2. I'll go ahead and bring that down. Let's talk about how to integrate x to the negative 8. Integration rules tell us to increase our exponent by 1 and to divide by our new exponent. Now that we're done integrating, let's not forget to add on our constant of integration plus c. And now I'm going to work on cleaning this expression up. So we have a 6. Negative 4/3 plus 1 is a negative 1/3. And then negative 8 plus 1 is a negative 7. Do not forget to keep that constant of integration. 6 divided by a negative 1/3 is the same thing as 6 times negative 3, which is a negative 18. I'm going to rewrite this x to the negative 1/3 by, for now I won't rewrite it. For now I'll leave it like this. Let's simplify here. We have a negative and a negative, which will give us a plus 2/7. And this x to the negative 7, I'm going to send to the denominator as an x to the 7th plus c. Actually, no, I'm not going to do that just yet. Sorry. I'm going to leave it like this for now. Because this, you'll see why I did this, right? I'm going to leave that there for now. But I would write my final answer without those negatives. So I would write my final answer as negative 18 divided by, and I put that divided by because I have that x to the negative 1/3. So that's the cube root of x in the denominator because it was negative, plus 2/7. And then I'm going to put an x to the 7th in the denominator because that exponent was negative, and I'll leave that plus c there. So there's our answer, but the reason I left this one like this is because this version here is already written very nicely for us to check our result by differentiation. So I'm going to take the derivative of that in order for us to check our answer. So let's take the derivative term by term. So starting with the first term, we need to pull that exponent of negative 1/3 down in front. Remember, we're doing derivatives now, not antiderivatives. So I'm going to pull this exponent of negative 1/3 down in front and multiply it with the negative 18. The new exponent on x, I need to subtract 1. Negative 1/3 minus 1 is negative 4/3. Moving on to our second term, we're going to pull that exponent of negative 7 down in front and multiply it with that 2/7. The new exponent on x would be negative 8 because we decreased our exponent by 1. And the derivative of any constant is 0, so I do not need to write that. And now I'm going to clean this up to make sure that it is exactly what we started with from back here. So multiplying negative 18 times a negative 1/3 would give us a positive 6. I'll leave this x to the negative 4/3. Here we have a 7 and a 7 that would cancel, but don't forget that this term is now negative, so I just have a minus 2, x to the negative 8th. So perfect, because this is exactly what we started with. So we have in fact verified that we did find a function whose derivative was what we had in our integrand to start off with. In example 9, it will be similar to example 6 because we're once again given an initial condition. So we still need to start off by integrating both sides and looking for the function f of x. To find the function f of x, we take the antiderivative of f prime. So I'm going to be integrating negative 2 sine x dx. I'll go ahead and pull that constant of negative 2 out in front of that integral. Let's go look at our integration rules to see how we integrate sine x dx. The antiderivative of sine is a negative cosine plus c. So we have negative 2 multiplied by negative cosine x plus c, which is a positive 2 cosine x plus c. So we did find a general solution, a family of solutions, that f of x is equal to 2 cosine x plus c. But that's not our answer because we are interested in, I do not just want some arbitrary c value. I want you to go and find the specific c value that when you plug 2 pi over 3 into the function, you will get out 0. So let's actually plug 2 pi over 3 into the function and set it equal to 0. So I have 2 cosine of 2 pi over 3. I'm plugging in 2 pi over 3 for that x, and I'm going to set all of this equal to 0. Right? So in this expression here, I replaced x with 2 pi over 3. I still kept the plus c. We're going to solve for that. And I set it equal to 0 because the initial condition said it should be equal to 0. It will not always be 0. Okay? It can be different numbers there. So going back to trigonometry, using what we know about the cosine function, cosine of 2 pi over 3 is a negative 1/2. So I'm left with negative 1 plus c is equal to 0, which implies that c is equal to a positive 1. So rather than giving this general solution with this arbitrary expression for c, I am particularly talking about the function where the c value is a positive 1. Our final example is going to be very similar to the last one, except that now we will have to integrate or take the antiderivative 2 separate times. And the reason that we'll have to do that is because in the differential equation, they did not give us the first derivative, they gave us the second derivative. So I can find the first derivative, I can find f prime of x by integrating the second derivative, right? Going backwards from the second derivative would give us the first derivative. So let's integrate 4x plus 3 dx. Starting with the first term, constant of 4 is going to stay. X currently has an exponent of 1. Antiderivatives tell us to increase that exponent by 1 and divide by the new exponent. Similarly, there's an x to the 0 here. The antiderivative of just 3 would be a 3x. Increase the exponent up to 1, divide by the new exponent, but we don't typically write that. And we do get a constant of integration. So we have integrated the second derivative in order to find the first derivative. So now that we have the first derivative, yet let's apply this initial condition that tells us that when you plug 1 into the first derivative, which is what I'm doing now, replacing all of the x's in the first derivative with 1, you should get out 10. So here I have 4 divided by 2, which is 2, plus 3, plus c is 10, which implies that c is equal to 5. So I now know that the first derivative, instead of having this arbitrary expression for c, I can replace that with 5. Our first derivative is 4x squared plus 3x plus 5. And now we are one step closer to finding our actual original function, because I can find the original function f of x by taking the antiderivative of the first derivative. So now we are going to be integrating 4x squared plus 3x plus 5, and we're doing it with respect to x. So let's start integrating term by term. First term, we have the constant of 4 that will stay there. We need to increase our exponent by 1 and divide by our new exponent. Second term has the constant of 3 that will stay there. We need to increase our exponent by 1 and divide by the new exponent. Final term has the constant of 5 that will stay there. We do not see an x, so we need to put 1, because that means there was an x to the 0. So we are increasing our exponent up to 1 and dividing by 1, which changes nothing. And of course, we will not be forgetting our constant of integration c. So this is what we have for our function f of x. We are not interested in this general arbitrary solution. We are interested in the particular solution that when we plug 2 into the function, so I am now going and replacing all of these x's with 2, we would get out 23. And now we will solve this equation for c. So we have 4 times 8 divided by 3 plus 3 times 4 divided by 2 plus 10 plus c is equal to 23. Gives us that c is equal to a negative 11 over 3. So now I will take this value of c and plug it into my function f. So I don't have this arbitrary general answer. Instead, I have the particular solution to this differential equation.